Okay, so let's begin. Welcome all. Welcome to the eighth lecture of this workshop, which is on Introduction to Matlab, right? Throughout this workshop, what we have learned is understanding the basic programming in Matlab. We started from learning various syntaxes of Matlab, how to perform basic tasks in Matlab. Then we looked at various decision loops and decision statements, functional loops, etc. in the MATLAB, right? And then after that, after learning that basic, we move forward with the chemical engineering problems. So far now, we have addressed uh, the problem of system of simultaneous linear equations. We have addressed the problem where we have non-linear equations in our system and how to solve that. So the last class we were looking at various examples which involved use of this non-linear equations in our system. So we looked at the example of flow through pipes where we had to use F solve to find the solution to find the friction factor from the Colebrook-White equation, right? We looked at the another example of the same where we had to find the first friction factor, and from that we computed the pressure drop in the pipe. Next, we look at the how to solve the uh, adiabatic flame temperature to find the maximum limit through the roots command, right? And a last problem was on the continuous stir tank reactor. For a steady state part, we had to find the optimum we have to find the reactor concentration or the outlet concentration for a given reactor volume, right? Now a couple of the corrections which I would like to begin with. So in the previous class when we were looking at the various solvers, we came across this portion where I had defined the function in terms of component x and y, right? And we were writing the function x and y. So we have defined this function in terms of x and y, and then we wanted to use fsolve to find the solution for this function by providing some initial guess value. We were encountering errors, right? So if I uncomment this portion and if I run it, so I'm getting an error here. So this error is coming because when we are passing the function to the fsolve, what it expect is the function has all the variables in that functions are of a single vector, right? In the sense that it does not take the multiple vectors as a as an independent variable. Rather, all the variables we have to provide in form of the same vector, right? So instead of doing that, instead of providing x and y as two separate variable, I will provide them as a part of one vector x, where component x1 will represent my x value, component x2 will represent my y value. When we do that and provide this function to f solver and provide the initial guess value, it is able to capture that, right? Because here what we have to provide is we have to provide the fsolve function value and the initial guess value. Now if I have multi variables function present, right? So x, y, let's say z also, so then I had to provide value for each. And fsolve does not it's not designed in that manner where you can provide x, y, z as a multi variable data, right? So whatever variables you have to provide, you have to provide it in one vector format only. So that's why a vector format, or let's say matrices format, anything, okay? So that's why you have to provide it into one go at this part only. Mm. So that's why this portion was not working. So remember this, when you are using fsolve and solving a function, okay, so that function has to be defined in terms of one independent variable. So this variable can be the vector also, it can be the matrix also. And then based on that, you can further differentiate your independent variables as a component of this vector x or matrix x, okay? That was one thing. Here we were getting some issue because I hadn't defined this equations correctly, but basically you have to define symbols x, y, and z, and then we were using the solve command to find the to find the symbolic solution of this given equation, right? So we wanted to find the intercept where we don't know the what is the variable x, what is the variable y, as well as we don't know the intercept. If we know the intercept, then it becomes a simple solution. But if we don't know the value of c, then that will all the solution will also depend what is my intercept c. And when I run it, so here I just get the solution. I am not printing it, right? So solution is symbolic, so that's why I get the sol part. And if I do display sol, so sol has two component x and y. So if I want to find the component x, I have to write display sol dot x. So I get this component. Y component is given as sol dot y, right? And here you can see they are written in terms of the x. Sorry, written in terms of the component c, constant c, right? Okay, and you have four types of solution possible, right? So this is your x and y, which is a combination of x and y represented in terms of c, then combination of x and y represented in this term of c, second line. Okay, so corresponding to x, y will be this, right? So that way you can find the solution. And another example that we were looking was on the steady state CSTR, right? So we were solving this steady state CSTR equation through the Epsol command, right? Where what we were doing is we were looking at the change in the volume of CSTR at an increment of 0.5 meter cube, right? And what should be the corresponding steady state concentration, right? And then we were not observing any change. The issue was that here what we were doing in this code was we had first defined the steady state CSTR function, right? So this function is defined in terms of the concentration x, sorry, not concentration, the conversion x, right? Where we are supplying the value of volume, flow rate, Ca0, right? And then we are asking it to solve such that fx solve for x such that fx equal to fx becomes 0, right? So here the issue was that once when I am defining this steady state CSTR equation, although the equation is defined in terms of this constant, the variable Ca0, Fa0, so its value is already predefined. So while defining this function, it takes this value. So when I run this command, control R. So here what is happening is, right? See, here you are getting CSTR defined in terms of this. Here you are looking at the variable names, but in actuality, we already have this variable defined. So when I'm updating the volume, V is equal to vol dot I, that volume value is not getting being updated in my CSTR ODE. Okay, CSTR, not ODE, CSTR equation, steady state equation, right? So it's working on this previous equation where the value of V is 2 meter cube only. So it's not updating anything because volume is fixed, so I will get the same answer, right? So when I'm updating the volume value, I have to redefine my CSTR steady state equation. So after updating the volume value, I am again rewriting the steady state CSTR equation. Okay, so it will update the CSTR equation based on the value of V, right? And then I'm using the fsol to find the steady state concentration. Okay, and then storing it. And when I do that, and if you will plot it, so this is how you will get a solution, that with increase in the volume your conversion is increasing. Okay, obviously it will depend. So this, in this case, we had a second order reaction. In case of first order reaction, you will get a different behavior, right? But it's with the change in the volume, you will get the change in the concentration or conversion, right? So that's one important factor, that when you are updating the any value of your function, okay, so you have to redefine that function again, right? So this were the two corrections, right? So in terms of the chemical engineering problems, what we looked so far are the system of simultaneous linear equations. Then we looked at the nonlinear equations and problem involving these two linear and nonlinear equation. Now in today's class, we will look at the solution to ODEs, which are ordinary differential equations, right? So when I say what are ordinary differential equations, differential equations are nothing but where your function involves the derivative, okay, derivative of any variable with respect to one independent variable, okay. So this is important aspect, that derivative with respect to one independent variable, right? um, so here, for example, derivative of y with respect to dt is given as combination of minus k times y, right? So here derivative of y is with respect to t only. So that's why it's an ordinary differential equation. When you have derivative with respect to the multivariable part, okay, multiple independent variable, so in that case it becomes a partial differential equation. In that case, the solution strategy will be different, that we will look at the later stage. Right now, we are focusing on the ordinary differential equation. And in this ordinary differential equation, the order will be determined based on the highest derivative order, right? So this is the first order uh, ordinary differential equation because you have only first order derivative, right? So if it would have been d square y by dt square, then it becomes the second order. Now, in this ordinary differential equation also, there are multiple types that you can count, linear versus non-linear, that will depend upon how your ODE is defined. Okay, if it's a combination of your linear dependent variable, then it will be the linear part. If it has some power, etc., then it becomes non-linear. Then you have single versus system of ordinary differential equation, right? So here I have dy by dt. So only one dependent variable y is given. But let's say I have two variable x and y, and I have dx by dt, dy by dt with time. Okay, so then it becomes system of ordinary differential equation where x and y values both are relying on the time. Then you have implicit versus explicit equation. Now, what does this mean? So this is important part. When I'm saying an implicit equation versus explicit, so the explicit part does not contain the independent variable, or its derivative in the function itself. So this comes when you are, why this is important, because this comes when you are doing the solution to this ordinary differential equation, whether the function is implicit or explicit, it becomes an important part. Let's look at some examples here so that it will become more clear. So if I look at the explicit, sorry, mm, not this way. Let me look at some examples, maybe from Wikipedia. Oh, it's a fairly big document. Anyway, the example that we can get. Hmm. I want an ODE example. Again, not here. No, this is in terms of the solution. So basically what it happens that the function itself contains the value of uh, independent variable also. So that becomes an implicit, and in the explicit, it's yeah, here. Hmm. So here this is an implicit function. In the explicit function, explicit differentiation is the standard method of differentiation where we directly differentiate a function that is explicitly solved for one variable in terms of the another. Not requires for y since y is a direct function of x. So this is the example where dy by dx here is given as 6 times x square plus 2. Right? So here, can you see this part that your differentiation this is an explicit equation. Now implicit part, your dependent variable is also coming on the right hand side, right? So here derivative dy by dx also contains the independent part as well as the dependent part. So when I'm solving this, I also have to take into account the dependent variable value. So this is implicit, and the explicit portion does not contain any dependent variable on the other side. So that is one example. Same way, then ordinary differential equation you can also define in terms of the initial value problems and the boundary value problems. So as a chemical engineer, we encounter both. So most of the reaction engineering problems that you will look are the ordinary differential equation initial value problems, and the boundary value problems are generally related to probably the flow conditions, heat transfers, etc., where you want to maintain certain boundaries values, right? So that in that case it becomes ODE boundary value problem, right? Now there is another term which is referred as stiff ordinary differential equation. So this stiff ordinary differential equation has a component that changes drastically at different rate, right? So let's say one way with respect to so you have two dependent variable y1 and y2, which derivative is given with respect to time. One variable y1 is changing very slowly with time, while another variable is changing very drastically with time, y2. So that becomes a stiff equation. Now again, why this is important, when we are solving this stiff ordinary differential equation, then which method you will use for the solution again will become an important aspect, right? So you have to also understand how your system behaves, how your ordinary differential equation value changes with respect to time, right? So that will help you to decide what kind of solution to use. Okay, so implicit solver helps to solve this stiff ordinary differential equation, right, which remains stable with a much larger step. We will come to that example also what exactly we are meaning. Now coming to the solution, so numerical methods you must have learned in your 11 12 standard or the UG curriculum, is that we use Euler's method and the Runge-Kutta method, right? So these are the methods where you solve the ordinary differential equation initial value problems, right? So let's look at the methodology for that part. In the Euler's So this is how the Euler's method is given, that you have function of function of y and t, right? So this is nothing but your differential part, right? This function f is your dy by dt. Okay, um, you have some value yn, you want to find what will be the next value of yn plus 1, right? So that you can find through this equation. Okay, so you are moving in time, so you know the one value at t equal to 0, you find what is the derivative at t equal to 0. Okay, through the function equation, and find what will be the value at t plus dt, right? So that way you move in the time. So this is your Euler's method. Okay, now this is an explicit Euler because you are only using the previous information here. Okay, there are some implicit Euler's method also. Okay, so in implicit method, as you can see here, in order to find what is the value at next step, okay, so yn plus 1 is given as, yeah, yn plus 1 is given as yn plus h time, h is your step size that you are moving, into your derivative at tn plus 1 and yn plus 1. Now in this case, see, your right hand side also contains the next variable value which we don't know yet, right? So then this becomes an kind of an optimization problem where you have to solve the function where LHS and RHS become same, right? So this is your implicit method, right? Same way, you have a Range Kutta method, RK method, to find the solution. So in RK method, what you do is you move ahead with this equation, right? So you must have seen this equation in your curriculum, right? That you find the value of k1 to k4. Each value is dependent on the previous value, right? So k1 is computed by function value at t and yn. You update the k2 value based on the k1 value part. Okay, here same way you move ahead with k3 k4, and then you put it into this equation and you get the next value, right? So this is your explicit Euler method. In the implicit method, again you will have this yn plus 1 term coming on the right hand side, so you have to solve it simultaneously to find the solution. Okay, don't worry, you won't go into the detailed methodological part, and even okay, yeah. So even in the today's class also we won't be going into the specific of this method. I have though provided you guys with the codes for this method. So you have Euler's method and the RK method. Right? There are certain examples that you can go through here. Right, so this is a homework problem statement for you guys, that you have to code the Euler's method and RK method and find the solution to ordinary differential equation initial value problems and compare your result with the inbuilt Matlab options. Right. So here are some of the examples. Basically, this is how the structure looks like. Let us quickly look at the Euler's method structure. That you define the function. Okay, so my function is dy by dx is equal to minus y. So function is defined. Here, see, I have two variables, t and y. Okay, so you might be wondering anyway that uh, t is time parameter is not coming into this equation. Why we are defining it? The reason is because as we are solving the part, the time component come into your ODE function. Okay, so ODE function here, yeah, time component comes in your my Euler method ODE function. Yeah, in your Euler method. So here I am coding the Euler method. Sorry, my mistake. So I have created one function, okay, which provides me the time and y value. So y value with respect to time. Creating it as a my Euler method. Provide the function value span, which is the time span over which I want to find the values, initial value of y0 and what should be the step size. Okay, so this is how they are defined. Once I know the time, I can find the next value as a previous value plus h times, calling that ODE function, providing the time and y value. Okay, now here, since the function is just an implicit function and it only is dependent on y, that's why we don't have to worry about the t part. But in cases you might have the function defined in terms of the independent variable also. So in that cases it's always better to provide both the dependent as well as the independent variable, regardless whether you are exactly using that value inside your ODE function or not, right? So I'm calling it, I'm moving ahead with time and just plotting it. So here I have plotted it with different step size. Okay. Yeah. So you can see the step size is also an important parameter. So if you have a bigger step size, then you will be losing the information. Your value might not be the correct. Okay. If your step size is small, then you are moving very finitely. So your next value will be more correct. So as you can see, if I move from step size from 1 to zero point 0.1, my curves becomes much smoother. I have multiple data points which are correlated to the previous value and I'm getting the smoother behavior. Right? Same way you can code it for the RK method and find out what are the values. Right? So this was this portion I am leaving up to you guys. You can try it out, and then compare your result with the MATLAB functions. So what are these MATLAB functions that we are talking about? So in MATLAB, to solve this ordinary differential equation initial value problem, you have multiple ODE functions available, right? So here, if I do help ODE, okay, it's not directly giving me this part. Okay, let me search ODE in the documentation. Yeah, choose an ODE solver. So here, it gives you the full description that what is ordinary differential equation, right? What are its order? What are types of different ODEs, right? So explicit ODEs, where your derivative is function of t and y. Implicit ODE is where your derivative is function of both t and y as well as your differential part here. So mty is the non-singular mass matrix. So it is dependent on your derivative or the next step also. Okay. So there are different further types also, which we are not going into too much, right? So basically implicit function will look like where your differential is a function of independent, dependent, as well as the derivative or the next value. Right? Now, further description is given, and yeah, here this table is important. So, what are various solvers that you have available in the MATLAB? So, you have ODE 45, 23, 113, ODE 15S, 23S, and how much accurate they are and when to use this solver. Okay, so for us as of now, for the learning purpose, this description or selection might not matter too much, but when you are solving very specific problems, specifically when you have this stiff ordinary differential equation where your one variable is changing very drastically with time, then you have to consider which function to use and how your accuracy is varying with this part. So let us look at the example of ODE 45 here. So this is how you provide the description of ODE 45. Right? So you have variable, you provide ODE 45, provide the function or your ordinary differential equations, temperature span over which you want to find the values, and the y0 which is the initial guess value. And in the output you get t and y data. So t is time, y is your dependent variable data. Okay. So here is the example is given that your differential is dy by dt is 2 times t. Okay. So you write ty is equal to OD45. Function is defined in terms of t and y. Okay. Template time span over which you want to compute. So here it's given 0 to 5 and initial value y0 value. So y0 0 is given. Okay. So you have put that and it computes t and y and then you can plot it and see how with time your y variable is changing. Okay. Same way here you have ODE 15s which is for stiff equation. So here some examples are given. Minus t dt. y1, y2. Just a minute. Mm, So this here is plotting one variable y. And they should have plotted both. Anyway, um, yeah. So this is used for the stiff equation where you can see the function value varies drastically for certain points, right? So here with respect to the variable y1, right? Your value here it's at this portion is decreasing linearly, and then for certain time span it's changing very drastically, and then again you have this kind of sinusoidal behavior. So there are certain points where the function value is changing drastically but for a small increment. So this becomes your stiff ordinary differential equation, right? In that cases you might need a much sensitive solution method, which is this. Okay. Here further description of this command is also given, what kind of method it uses, etc. You can check it out. Okay. So let's look at some examples that I have cultivated. Right. So these are the various ordinary differential equations. Right. So first let's look at the non-stiff problem that we have seen, that your dy by dt is -1 by I'm creating a function in terms of t and y. Find using the ODE 45, supply the function value, the time span I am giving between 0 to 5. Initial guess I have given as 1. And if I run it, yeah, this is my figure 1. Okay. So it plots y from ODE 45 versus time. And you can see it's decreasing this way. So with time, I know how the function is decreasing because it's -y, so it's declining, right? Then let's say you have uh, two variables ordinary differential equation, right? So you have derivative with respect to y1 and sorry, you have derivative of y1 with respect to time as well as y2 with respect to time, and these two equations are given in this form. Okay. So now this is a stiff ordinary differential equation, so that's why I written a stiff function. Okay. And here I'm providing the creating the function in terms of t and y. The first equation, so first row represents my first equation, right? -0.1. Here see, the y1 and y2 are defined in terms of the one vector only. Okay, so I'm creating the y vector. Its first component is y1, second component is y2. I cannot do x and y here because again the solver, the way it works, it expects only the one it expects the only the one vector or the matrix where all the dependent variables are there, right? So this is important part. I cannot create y1 and y2 two separate dependent uh, dependent variables. The function will work in that way, but when I will supply to this ODE 45, like the fsolve part, it will throw an error. Okay, so here I have find it, so I'm using both OD 45. Okay, I'm supplying the strip function to find the solution, plotting it, plotting y1 and y2. In that case, you get this figure 2. So here you can see the variable y1, which is this blue line. Okay, it's changing gradually with respect to time. But variable y2, can you see from 1 it has drastically gone down to 0, right? And then it's remaining close to 0 throughout the time span. So this is referred as stiff part. One part is changing gradually, the second part is changing the drastically. Then, yeah. So here the same way I have used OD15 as command. Now each of these function uses a different set of a method, right? So since it's a OD15s is specifically designed for stiff OD, it works much faster, right? So here I am using this stick talk command, right, which we had discussed previously also, that in TikTok command what it does, it helps you to find how much time has passed from starting from the first event of tick, right? So I'm finding how much time it takes to for OD45 to solve this function, and how much time it takes for OD in 15s to solve this function. And when you run it, what you get is this. See, that OD45 took only 0.68 second with 6,000 steps, while OD15s, which is optimized for stiff ordinary differential equation, use 92 steps. Okay, you can learn more about this command through the help part. So OD45 here, yeah, yeah. So this is the given OD 23, 45, 78 are all single step solver that uses explicit Runge-Kutta method formula for different orders to estimate the error in each step. Right? Compared to that, if I do OD 15S, okay, its entire description is given here, which kind of method is it uses, right? So here it does some Jacobian computation, etc., to find the solution. Again, we don't have to go into this details, what exactly this are, but these are the certain things that you have to keep in mind that depending upon what sort of a function you have, you have to use that particular method. Again, here we are not dealing with much of a very complex problem, so that we don't have to worry about it. Okay, but still there are certain cases where you might have to think about what kind of method you use, right? So with this logic in mind, that when we know how to solve ordinary differential equation through the inbuilt MATLAB commands, right? Let's look at the chemical engineering problem which involves ordinary differential equation use and how we can solve it. So we have an example of unsteady state CSTR. So in the previous class, what we had seen was the steady state reactor where the differential component was zero, right? So dC by dt we had considered zero. Okay, so here we have given that you are a process engineer who is assigned a task to manage an exothermic reaction in CSTR. The product is a high value specialty chemical. The reactant fluctuation in the cooling water supply temperature causes an increase in the reactor temperature. Okay, sorry, the recent fluctuation in the cooling water supply causes an increase in the reactor temperature, which is not recommended as the product starts to degrade if exposed to more than 2 minutes at temperature above 350 Kelvin. To avoid such scenario in the future, you have to simulate the dynamic response of the reactor to a step change in the coolant temperature Tc, perform a sensitivity analysis to determine what is the maximum safe limit for the coolant which prevents the thermal decay, right? So we have some thermal temperature fluctuation in the cooling water supply which has created the spike in the reactor temperature. Now you want to understand based on this experience what maximum limit of cooling temperature increase we can go which will not degrade my product, right? And the degradation criteria is given that if your uh, components are exposed to temperature above 315 Kelvin for more than 2 minutes, that means they will start degrading. Okay. The CSTR data is given. You have feed volume, feed volumetric flow rate, reactor volume, concentrations, temperatures. The reaction data is also given, right? Cooling water information is given. So we have to consider cooling water normal working temperature is 285 Kelvin, and we have to consider an increase in the coolant temperature up to 300 Kelvin. Now, so for the CSTR, if you will perform mass balance and energy balance part, right? So this is how it will look for an unsteady state component. So in the previous lecture, we saw we had only this portion where dCA by dt we had considered zero, right? Because it was steady state. We also did not consider the time component part, right? But right now we have both mass balance as well as at the energy balance. So in mass balance, you get dCA by dt is equal to this portion where you have rate of reaction coming into the picture. In your energy balance, change in the temperature of CSTR with respect to time is given by this. So this is nothing but your heat in minus heat out plus generation that is occurring because of the reactor minus the energy that you are taking out from the reactor. Okay. Rate of reaction is given as K exponent minus EA by RT into CA. So here one thing to note is that your rate part also includes the temperature. Okay. So in order to compute the CA, you are dependent on the temperature. In order to compute the temperature, you are dependent on the uh, temperature as well as the concentration part also see, right? So it's a coupled ordinary differential equation because both ca and temperature are dependent on each other, right? So it's not an independent way. If they were independent, let's say dca by dt did not include any temperature part, right, in that case they will become separate. So I could solve the dca by dt independent of temperature, but here both temperature and the reactor concentration are dependent on each other. So that's why it's called the coupled ordinary differential equation. So we have to solve the system of ordinary differential equation multiple times, each with different cooling water temperature, and analyze how reactor temperature varies and what will be the maximum safe limit as well as how conversion is getting affected. Right? So this is our task. Then we will code it. Okay. Just give me 1 minute, please. Okay. So, since we are already out of time, I mean, it's 15 minutes are only left. I won't be fully coding this problem because it will take much longer time. Rather than that, I will show you the description from the sample script today, right? And then we will discuss it line by line, right? So first, the starting of script, I am removing all the previous variable, closing all the figures, clearing out the command prompt. You can do CLF also. So CLF will remove all the figures, close all the figures. Okay. So this is what you have done it. Now, first step will be to list out all the given data that we have. Okay. So for a CSTR, what information is given to us? We have been given the feed data, reactor data, kinetic data, right? So I am putting it out that feed volumetric flow rate is given as 10 meter cube per minute. Reactor volume is 20 meter cube. Concentration is 2 kilomole per meter cube. So I am writing 2 kilomole per meter cube. Temperature T0 is 310 Kelvin. Okay. So T0 is a feed inlet temperature. So that's why I'm referring at T0. Now, reaction kinetic parameters. So K0 value is given, which is 5 into 10 to the power 6 per minute. Okay, so it's very high value. Now, based on this, what kind of order this reaction has? Can you think about it? Right. So, based on the unit, it's a first order reaction. Okay. Activation energy is given, which we have written it out. Gas constant and the heat of reaction. So heat of reaction is given as -2 into 10 to the power 5 joule per mole. This is an exothermic reaction. Then thermophysical property for the fluid is given as your density is 500 kg per meter cube, Cp value is 75, the heat transfer coefficient into the area UA is given as 5 into 10 to the power 4. Okay, so this is overall heat transfer coefficient into the area. Then the cooling temperature, original temperature, which is the base temperature, so Tc original is given as 285 this much Kelvin. Okay. Now what we will consider is, so this Tc original and this initial concentration Ca0, these are your initial value, that is that or the steady state value that are present in the reactor. Okay, so that's why I'm referring as them as Ca initial and T initial. So this is before uh, introducing any perturbation in your system, right? So Ca initial is Ca0, T initial is T0. So my initial value becomes y as a function of y0 is Ca initial, T initial. Let's say time span you have to decide. So right now I have considered, so it's a first order reaction and the K0 is very much high. So I am selecting time span of 0 to 50. Why exactly this time span? I will come to that also when we run the simulation, then you will understand. Okay? But basically it's decided based on where you will reach the steady state part. I have to define the CSTR ordinary differential equation. Right? So I am writing CSTR OD, which will be the function of my time, function of my concentration and temperature, as well as cooling temperature Tc, right? So here in the CSTR ODE, what are my dependent variables? Ca and time. What is my independent, sorry, Ca and temperature. These two are my dependent variables. What is my independent variable? So that is time, right? So these two are written. Also, we will be varying the temperature Tc here, okay? So that's why I am creating function as a part a function as a function of the TC also, right? OD differential are created as a function of TC also. Let's say instead of TC you might had a uh, idea that you want to vary the UA. Okay, so in that case your function will be written in terms of the UA, heat transfer coefficient into area, right? So these are the things you have to consider. Now I have two equations, so I have written it out. So first equation is for my mass balance, which says this: Fa by V into Ca0 minus Y1. So Y1 is my concentration part minus K rate part, okay, is equal to 0. So minus K exponential minus EA by RT into Y1. Then the second part is FVT0 minus Y2 minus uh, heat of generation plus heat of removal. Okay. So same equation we have just written in terms of the variables, right? Once you have defined this equation, right? Now we have to see how cooling temperature affects my CSTR. So I will consider different TC test values from 285 to 300 Kelvin. Okay. So from 285 to 300 Kelvin, we are considering various values. This part, it just creates various color gradients, since for all temperature value we will be plotting something. So this is just to use the color to get generate a color map. You don't have to provide this. I mean, by default, when we are plotting multiple graphs or multiple curves on the same figure, Matlab will select a new color all the time, right? So this is just an additional step, right? Now for each TC, I will get some steady state temperature value. For each TC, I will get some steady state concentration value, right? So I'm creating a vector T temperature and Ca. So temperature steady state value, concentration steady state value. Its size will be exactly how many TC values I have, right? So I created a zero vector which has a size of TC test. Same way for the concentration also. This is just a figure definition part. Now what we will do, for each temperature, we will solve this ordinary differential equation and find what is the steady state temperature value. Okay. So for I is equal to 1 to the length of Tc test value, I am defining what is my current cooling water temperature, right? So I am going over the length of Tc value. So this is my for loop which works on the I and goes to the maximum component. So 1, 2, 3, 4, 5, 6, and 7 value it will go. Right? Here, so Tc current value will be Tc test value of I. So I is equal to 1. So first value will be at 285. Okay. Now for this 285, I have to update my ordinary differential equation. So here CSTR OD, it was a part of the function of time, my dependent variable concentration temperature, and the cooling water temperature. Now I have fixed the cooling water temperature Tc. So what I will do, I will create one new function which I am referring as current OT is that calls the temperature, sorry, that calls the independent variable and the dependent variable, calls the CSTR and provides the Tc current temperature. So this third variable that we had for our original ordinary differential equation is fixed. Okay. So I get this current updated ordinary differential equation. Then I am calling ODE 45 to solve this equations. Okay. So ODE 45 we have called, we have supplied the ODE temperature span which we have already defined from 0 to 50. Initial conditions are given CA0 and T0 values for the feed, right? It will compute the variation in the concentration as well as the temperature of reactor with time. Okay. Now I have to extract this data. So here previously what we said that y vector y contains the concentration as well as temperature. So y1 is your concentration, y2 is your temperature. Okay. So I'm taking out that data only. That first column of my y, okay, is my concentration. Second column of my y is my temperature. So I'm taking it out. Steady state will be reached once your fluctuation will end, right? So the end value of Ca and T reactor, okay, the end value of Ca and end value of T reactor, I am referring them as a steady state, and that steady state for a corresponding Tc value. So I am storing it them. Okay. Then you can do a subplot where I am plotting the change in the reactor temperature with time, right? So this is plot T versus T reactor. Again, this color part and these things are just for a beautification. If you don't provide this color portion, it will automatically take some new color, so you don't have to worry about it. Line width I am controlling. I am displaying the name which says Tc is equal to %dk, where I am supplying the current temperature values. Okay. Hold on is on so that multiple plots will be done. Then subplot 1 comma 2 comma 2. Second subplot is change in the concentration with time. Okay. Again, color part you don't have to worry. These are the additional steps for the beautification. Okay. So for one Tc value, it will compute the ordinary differential equation, solve it, and you will get the steady state value, right? Over all temperature loop it will do, and you will get one plot. Then you also have, now further, once these calculations are done, again some beautification is done on the graph where I am providing the title label to x and y axis. Okay. Here this part is important, that we have been given that we have a maximum temperature safety limit of 315 Kelvin, right? So I'm creating Y line which is 315, okay, labeling it as maximum safe temperature, right? Just this are the just label how to put that at particular location, okay? Just read about it in the description or the help manual. You will understand what exactly this means, okay? So this is again the beautification part or the naming part that we are doing, right? And afterwards, what we are doing, I'm also creating a new figure which does the sensitivity analysis, where we look at the how steady state temperature changes with respect to the cooling water temperature. So it's a plot of Tc versus T. Okay, same way how steady state concentration conversion changes with the Tc value, right? Again, I will come to this part in the second in seconds, but let's run this loop and see how what we are getting in figure 1. Yeah. So here, this is your part. So as you can see, I had created a subplot, right? We had subplot 1 comma 2 comma 1. So one row, two column, and this is first column and the second column. First column was for the temperature, second column was for the concentration. Can you see it? The first column, the first graph is for the temperature, second is for the concentration. Here what we are seeing that it's a first order reaction, very fast reaction. So you can see reactant A is converting as soon as it enters in the reactor, and its concentration goes down and it reaches the steady state value, right? So that is one observation. Another observation is as the reactant enters in the reactor, the temperature of the reactor is increasing, but because of the presence of cooling water, because of the jacketing that has been done around it, its temperature goes down gradually. And this specific increase is also because of the exothermicity of the reaction, right? So as soon as the reactor enters, your reaction conversion starts, okay, concentrations are decreasing, and heat of reaction increases the temperature of your reactor. But since we have the cooling temperature, it will bring down the temperature of the reactor down, and at after some time you will get the steady state. So here first thing comes that the temperature span that we selected from 0 to 50. So that is not just based on the intuition. You have to run one ODE, and you have to run your ODE at one specific temperature or any specific temperature and see how your system behaves when the equilibrium is achieved. Since it's a faster reaction, your equilibrium is achieved somewhere around 10 to 20 minutes, right? But let's say it was a slow reaction, then your equilibrium might not have achieved around 50 minutes. Then you might have to increase your temperature span to, let's say, 100 or 150 minutes to see whether steady state has been achieved or not. Let's say in this case, if I had selected the temperature spans from 0 to 5 minutes, then it's not correct, because if I just only look at this part, still my reactor temperature is varying, still my concentration is varying, right? It is after 20 minutes or so that it reaches the steady state value. So that's why I cannot select much lower temperature. So what range to select to find the steady state, that is also an important aspect that you have to consider. So for that, ideally what I will do is I will select one temperature, let's say 285, run the ODE for different time span and see where the steady state is achieved. And for the next case, I can just select that time span. Okay. Now, here, what is happening, what observation we had was how the increase in the cooling water temperature affects your reactor temperature. So here you can see, as I increase the cooling water temperature from 285 to 290, 290 to 293, you can see overall reactor temperature is increasing because obviously cooling, since the cooling water temperature or the coolant temperature is low, the heat removal from the reactor is low. But there is this spike specifically that we have to look for, and that spike, uh, yeah, can you see? So our maximum safety temperature is 315 Kelvin. So if my cooling water temperature is 285, I am okay. If my cooling water temperature is 290, okay, so in that 290 only, I am crossing the temperature mark of 315 Kelvin, right? So that's a danger sign. But what we have been mentioned was that if exposed to more than 2 minutes to temperature 315 Kelvin, then your product will start degrading. Here the temperature is increasing, but it's coming down much faster also, right? So maybe you have to look at this specific time span, this specific time range in which it's going above 350 and coming down to 315 Kelvin. If it's this time limit is less than 2 minutes, then you are okay. Else, for the other cases, like in the case of 300 Kelvin, you can see if temperature is increasing, I'm not never coming below 315 Kelvin. So my product will degrade. For other cases of let's say 295 or 294 or 293, there is this spike. But obviously you can see at 295, after spike is coming down, but the time span in which it's coming down is more than 2 minutes, right? From 0 to let's say somewhere around 1 to 5 minutes. So it's 4 minute time span in which my product will degrade. So maybe I can go to my temperature of let's say 290, where the temperature is increasing slightly above 315, but it's coming much down much faster. My cooling water is maintaining the temperature below the thermal degradation part, right? So this is one observation. The second plot that we had done is, so it looks at, it is a two axis plot where on the left hand side I am looking at the steady state temperature, change in the steady state temperature with respect to Tc, and on the right hand side I'm looking at the conversion. So what I'm finding is, since it's a first order reaction and it's a very fast reaction, and with the K0 value much higher, you can see regardless of changing the Tc value, my conversion is not getting affected too much, right? So it's close to 70% conversion only. My steady state temperature though is increasing much faster because of the exothermicity of the reaction, but the conversion is not yet affected too much. Okay, so that is the information that I can infer, right? And this plot part here, so since I want to create two y-axis, so what we are doing, we are creating one figure. I am writing y-axis left, so this will create y-axis which only with the left portion, with the left y-axis as a reference, it will plot the Tc versus T steady state value. I'm giving it label. So all things will be with respect to the left y-axis. Okay. I'm plotting this y equal to 315 Kelvin line also. Then I'm writing y-axis right. So it will create a secondary y-axis on the right hand side, and then after I'm finding the conversion and plotting that conversion with respect to Tc. Okay, so this will be plotted with the right axis. Okay, you can provide limit etc, and then provide the title and run the command. Okay, all the variables are also stored in between. So let's say if I want to find steady state temperatures, these are the values. Okay, at the end, if I want to find the conversion, steady state conversion, so CA steady state. So this is the concentration, and conversion X will be, which variable we are using for the conversion. Okay, I'm not storing the conversion, but it's just C. So for final, this is the conversion part, yes. 60 to 70. So it's barely have changed. It's increasing because the reaction is faster and it's helping. But you know, for the exothermic reaction, initial increase will help in the reaction, but afterwards you will find a decrease because of the exothermicity of the reaction, right? So if I run it, I get it plot in this manner. Okay. Yeah. So this is how you can, troubleshoot or understand your system, how it behaves with different, sorry, how it behaves with different perturbation. Okay. The same way you can look at if you want to change the, let's say, feed flow rate or the reactor volume or the inlet concentration, how it will affect your overall dynamics, right? So such sensitivity analysis can be done through Matlab. Okay. Mm. So that's it for the today's class. I mean, we looked at the ordinary differential equations, its solution, how it's done. So numerically, we know the Euler's method and the RK method, right? Through Matlab, we can find the solution by various ODE functions that we have already available. Okay, you can compare your solution. You can compare this ODE Euler's method and the RK method with the ODE functions that you have already available. These are the very basic simple methods, and you have already seen it somewhere in your curriculum, so it should be easy to understand. And with that logic in mind, we solve the CSTR problem, unsteady state CSTR problem, which involve the solution to the simultaneous, which involve the solution to this coupled ordinary differential equation. And based on that, how we can troubleshoot any problems that we have, right? So overall logic remains as it is, that you see the problem, you define your system in certain sort of a mathematical form, mathematical equation based on the physics of that problem, right? So in our case, we already know that the mass balance and energy balance of CSTR for unsteady state part looks like this. Now you categorize what kind of this numerical equations are this. So we know these are the coupled ordinary differential equation. So that is second step, identifying what equations you have. Third step is how to solve that equations. So we are using numerical methods to solve these equations, and we are using relying on the inbuilt MATLAB functions, right? So that is third part, and fourth part is the execution part, where you use that solvers, whatever methods you have, to find to find the final values or the output based on whatever input you have. Okay, so that's it for today's class. Do look into this examples, try to understand. If you have any query, do reach out to me. Okay, in the next class we will solve some more examples of ordinary differential equation. I will try to see if we can include partial differential equation here or not. If not, then maybe in next to next class we will look into that. Again, it will require some understanding, but I think we can do it. Yeah. So thank you for joining.